Venkatrakrishnan, shall we start?
Yes.
Yes.
I'm available. Yeah.
Good afternoon to one and all present here. I'm Dr. B. Kavita, Assistant Professor, Department DBT Coordinator from GVG Visalakshmi College for Women, Udmalpet. And today, the final day of our FDP on development of materials characterization techniques and their future prospects, organized by our Department of Physics under DBT STAR status scheme. The main aim of our FDP is to enrich the knowledge of faculties through interaction with eminent personalities from reputed institutions and academics. The knowledge sharing will improve the teaching learning process to the students and benefit the society. Apart from the teaching learning process, faculties should enhance and equip them with sufficient knowledge in emerging techniques in their research areas. With this point, we organized a faculty development program towards characterization prospects. Now it's my immense pleasure to welcome you all for the today's session from various institutions. And it's time to welcome our chief guest, Professor Venkatrakrishnan. Professor Venkatrakrishnan completed his PhD in chemistry in the year 2006 from University of Stuttgart, Germany, after completing his BSc and MSc degrees from PSG College of Technology, Coimbatore. Subsequently, he worked as a postdoctoral researcher at University of Pennsylvania, USA, from 2006 to 2010, and then as a research associate at National Institute for Material Science, Shikaba, Japan, from 2010 to 2012. He joined as faculty at the Indian Institute of Technology, IIT Mandi, in April 2012 and is currently as a full professor. His research group is mainly working in the field of green chemistry and heterogeneous catalysis for energy and environmental applications. Successfully guided 11 PhD and 26 MSc students and is currently guiding 7 PhD and 7 MSc students, in addition to several short-term research interns. He has published more than 180 articles in well-reputed international journals and is also a reviewer for several scientific journals. He is currently serving as the associate editor of the New Journal of Chemistry, published by the Royal Chemical Society, and is also on the editorial advisor board of ACS and ESNT Engineering Journal, published by the American Chemical Society. Yes, Professor Venkatrakrishnan has been bestowed with several awards, including DST Inspire Faculty Award, IIT Mandi Foundation Day Award for Excellence in Teaching, MANA Research Fellowship, DOE Postdoctoral Fellowship, DFG Doctoral Fellowship, Scholar Fellowship, etc. In addition to teaching and research, he has also served IIT Mandi in various administrative positions, such as first warden of the hostel in main campus, founding coordinator of Advanced Materials Research Center, associate dean research, and most recently as a dean of sponsored research, industrial consultancy, and international relations, and director of IIT Mandi Catalyst, and director of IIT Mandi ICUB and HCI Foundation. Apart from academics, he likes reading books and is interested in linguistics. A warm welcome to Professor Venkatrakrishnan, and he is my best friend. I'm very happy to invite you for this session.
Thank you, Kavita, for a very detailed introduction and also for the kind invitation. So, by the way, Kavita did not mention that we both were classmates at our MSc program. So we both did our MSc together jointly at the same time. So let me share my screen and start the presentation. If I get disconnected or something, please give me a call. Once it happened in an online presentation that I kept on talking and later I realized that I was disconnected for whatever reasons. So please give me a call in case there is an issue.
Okay,
So
okay.
today I will be talking about heterogeneous catalysis for energy and environment applications. I know that this faculty development program is mainly for different techniques. So here in this work, I'll talk something about our research work, and also I will connect with the various different techniques which we have used for characterization of the materials, and I'll also talk about some of the applications here. So since Kavita already read out the introduction, I'm not going into it. For those of you who might be wondering where IIT Mandi is located, so IIT Mandi is located in the northern North India, in the state of Himachal Pradesh. So Mandi is located exactly at the center of Himachal Pradesh. It's a relatively a small town. Interestingly, it cares latitude or longitude, whatever this is called as, it kind of passes through Coimbatore in Tamil Nadu. That's very interesting coincidence. And our institute IIT Mandi is kind of spread across a very beautiful terrain, a hilly terrain. This is what we call it the South Campus, and this is the North Campus. And in fact, we also own this hill which is in between these two campuses. So it's spread across around 538 acres of land. It's quite a big and beautiful campus. Our campus was established in the year 2009, and we currently have about 2,800 student members. Then these are some of the buildings in our campus, and this is where one of our labs is being located. So first and foremost, I would like to acknowledge all the members of my research group who have done all the works, and I'm in front of you presenting their works. In today's talk, I'll just give a brief overview of the research work done by 5 of my recently graduated PhD scholars, Dr. Tripti Chabra, Dr. Priyanka Chaudhary, Dr. Hussein Chand, Dr. Ajay Kumar, and Dr. Ashish Kumar. Our group is actively working in the area of heterogeneous catalysis for energy and environment applications. And within this domain, we work on a couple of applications which involve biomass conversion, wherein we take the waste biomass and get it converted to something useful products. But at different places in India and also abroad, there are different type of biomass waste one can see. For example, in certain areas, the sugarcane bagasse is a biomass, and in the northern India, the wheat husk is a biomass. Whereas in southern India, the rice husk and the stubble could also be a biomass. So we can kind of get a lot of biomass derived compounds which can be converted into more useful products. So that is one area of research which we are doing. Another is the green organic transformation, wherein we take certain industrially important organic transformation reactions, and we tend to develop some processes and procedures wherein we can do the same reactions in a green and sustainable way. Green means environment friendly way. Another is the carbon dioxide reduction, wherein we kind of convert the carbon dioxide into other useful products such as cyclic carbonates. And these 3 areas we are doing it thermocatalytically. And another 3 more areas wherein we do the hydrogen evolution, pollutant degradation, and nitrogen fixation. These 3 we do it photocatalytically. And hydrogen evolution, what we are trying to do is hydrogen is a fuel for the future. So there are many efforts which are going on from the government of India side, and also from several industries on in green hydrogen. So basically, we can obtain green hydrogen from water, because water, when we see the structure of water, it's H2O. The H2O can be split into hydrogen and oxygen, and the evolved hydrogen can be used for different applications. And in order to do this, we need a light, and also we need a catalyst. So that's what we develop a catalyst, and we can use the direct sunlight in order to split the water into hydrogen and oxygen, and the evolved hydrogen can be used for the energy application. Another is the pollutant degradation. So in many places, like in Tirupur and other areas, there are a lot of textile industries which generate a lot of colored waste. And these colored waste are the organic molecules, long organic molecules. And we can kind of chop this organic molecules into much smaller fragments, which are non-toxic in nature. So this is what we do it on pollutant degradation. Another is the nitrogen fixation. Nitrogen fixation involves conversion of nitrogen to ammonia. So nitrogen N2 molecule is converted into NH3 molecule, which is the ammonia. And ammonia, as we know, it's a very important chemical which is used in fertilizer industry, in pharmaceutical industry. It has several uses. And till date, the only process which is used for the preparation of ammonia is the well-known Haber-Bosch process, which was invented in 1935. But we need to optimize the many other processes as well, because the Haber-Bosch process is not sustainable because of the high energy requirements and also the high CO2 emission emission which this process is producing. So what we are developing is a type of a catalyst which can kind of do this nitrogen fixation, that it can convert nitrogen to ammonia, wherein nitrogen can be obtained from the air because 78% of the nitrogen is in the air, and then the hydrogen can come from water because of the water splitting, and these two can be combined together in the presence of sunlight, which is another abundant resource, to form ammonia. So that's what we are doing in this case. Now comes the question why there's a need for sustainable development. So when we look at the conventional approach uses expensive metal-based catalyst, high temperature, high pressure, harmful solvents, toxic reagents, and the entire process is quite difficult to handle. On the other hand, when we look at the sustainable approach, we can use metal-free in the inexpensive catalyst, mild reaction conditions wherein we can use low temperature and atmospheric pressure for the catalytic reactions. We can use environmentally benign solvents which are non-toxic in nature, and also we can reduce the waste and which can have less detrimental impact on the environment. So there is a very strong need for the sustainable development. And how to achieve sustainable development. So since our group is working actively in the area of heterogeneous catalysis, so we kind of self-impose certain constraints on how a catalyst has to be designed and how we want to utilize that catalyst. So some of the design constraints which we apply on to ourselves are use of earth-abundant elements for doing the catalysis, predominantly metal-free elements and also low-cost materials, and use of non-toxic and non-polluting chemicals and processes for the entire catalytic cycle. Then use of relatively low temperature, that is less than 250 degree for the catalytic reaction. Use of ambient pressure, which is the normal atmospheric pressure for the different catalytic reaction. So for this matter, we have never purchased a pressure reactor to do the pressurized reactions under pressurized condition. We normally use this atmospheric pressure for the catalytic reactions. And adherence to all the green chemistry principles to the best extent feasible. There are 12 green chemistry principles, which I'll show it in the next slide, which we tend to adhere to the best extent feasible. And thereby, we would like to cater to the relevant United Nations Sustainable Development Goals. I'll also show you what are the different United Nations Sustainable Development Goals. So these are the 12 green chemistry principles. It's most of you may be already aware of it. It's from our textbook. So the 12 green chemistry principles are waste prevention, atom economy, less hazardous chemical synthesis, design of safer chemicals, safer solvents and auxiliaries, design for energy efficiency, use of renewable feedstocks, reduce derivatives, catalyst, that is use of catalyst, design for degradation, real-time pollution prevention, and safer chemistry for accident prevention. So these are the 12 green chemistry principles, and we would like to adhere to all the green chemistry principles in our research works. And these are the 17 United Nations Sustainable Development Goals, which is in short called as the UN Sustainable Development Goals. And among these 17 goals, we particularly cater to 5 of them, which include clean water and sanitation, affordable and clean energy, responsible consumption and production, climate action, and partnership for the goals. Now moving on to the main material which we use as the catalyst, which is this material called as the graphitic carbon nitride. And just the name itself, it indicates that this material possesses carbon and nitrogen, both of which are earth-abundant elements. And this graphitic name comes because they have arranged in a type of a pattern called as the cis-triazine-based pattern, which kind of gives its name as graphitic because the graphene sheets are also arranged in a similar pattern. And this material, the graphitic carbon nitride, can be easily synthesized by polymerization reaction of cyanamide, dicyandiamide, melamine, or urea. Any of these can be used as a precursor. By using a very simple polymerization reaction, we can prepare this material, graphitic carbon nitride. And the prepared graphitic carbon nitride is stable both chemically as well as thermally. Chemically stable means if we kind of treat it with harsh conditions like harsh acid or harsh base or some harsh solvent, it will not get destabilized. At the same time, when we heat it to a slightly higher temperature like 400 or 450 degrees centigrade, it will still retain its structural integrity. So that thereby it indicates that this material is thermally stable. So it is both chemically as well as thermally stable. And another beautiful thing about this material is amenable for surface functionalization. So we can kind of functionalize this material with surface functional groups like SO3H groups. SO3H is the sulfonyl groups or phosphate groups, nitrile groups. You can kind of functionalize it with many different groups. At the same time, if you want to do doping, we can also dope this material either at the carbon site or at the nitrogen site with any other heteroatom such as boron or any other atom. Now moving to the first part of my talk, which is the first application, which is on biomass valorization. So as I said, biomass is the waste materials which are found from the bioresources, like which include sugarcane bagasse. After the sugarcane juice is being extracted, it's a waste. The stubble, which includes the haystacks from wheat and rice. So that is also a biomass waste. So that can be converted into something which is useful. So this is kind of a lot of reactions come under this biomass conversion. And one of the most important reaction in biomass conversion is the conversion of saccharides to 5-hydroxy methyl furfural, which is in short called as 5-HMF. So this is one of the important conversion. And what we have done is we have done this conversion in green solvents. Green means environment friendly solvents, by using a particular catalyst. We have designed this catalyst, which is called as the sulfonated graphitic carbon nitride catalyst. And we have designed this catalyst to so that the single catalyst possesses both Bronsted base sites as well as Bronsted acid sites. The Bronsted base sites originate from the nitrogen moieties which are present in the graphitic carbon nitride, and the Bronsted acid site comes from the sulfonyl groups, SO3H groups, which are functionalized onto this graphitic carbon nitride. And we have utilized this catalyst to convert saccharides to 5-HMF selectively. Selectively means this is the one and only product which is formed during that reaction. And we have utilized different type of saccharides, which includes the monosaccharides such as the glucose and fructose, and also the higher saccharides which include cellulose, sucrose, and starch. So we have utilized many different type of saccharides and converted them all into one single product, which is the 5-HMF. And we have utilized several different green solvents, which includes water, ethanol, isopropyl alcohol, and dimethyl carbonate. And finally, the obtained 5-HMF, because 5-HMF is a platform chemical. Platform chemical means it's a chemical where we get that chemical, and from that chemical, we can get more other chemicals as well, like which can be used in pharmaceutical, nutraceutical, or even as a jet fuel. We can use many different chemicals. So we have utilized this 5-HMF to convert it into other value-added products such as 2,5-bis hydroxymethylfuran, 5-chloromethylfurfural, and 5-bromomethylfurfural. And whenever we prepare a catalyst, we need to ensure that the catalyst is properly characterized so that we understand the successful synthesis of the catalyst or whether the catalyst is successfully prepared or somewhere some issue has come. So in order to do that, we need to characterize it with various different techniques. And I know that you have already gone through many different techniques as a part of this FDP. So you might be already familiar with many of these techniques. So one of the techniques is the X-ray diffraction, which can kind of indicate whether the material is crystalline or not, and where the peaks are coming. And we can compare the peaks of this graphitic carbon nitride with those of other graphitic carbon nitride which are already reported in literature to get an idea about whether the material preparation is successful or not. And the other techniques are the Raman spectroscopic technique and FDR spectroscopic technique, with both of which are vibration comes under the vibrational spectroscopic technique, which indicate what type of functional groups are present on this material. So we have functionalized it with sulfonyl groups. So from these two techniques, we are able to decipher that sulfonyl functional groups are present in the material. Then we have done the thermogravimetric analysis, which indicates that what is the thermal stability of the material. The graphitic carbon nitride material, the bare graphitic carbon nitride, this is quite stable to about 550 degrees C, whereas the sulfonyl functionalized graphitic carbon nitride material is stable to about 400 or 450 degrees C. This is still a very good temperature because we in our reactions, we hardly go below 250 degrees centigrade. Then another property is what is the physical feature or what is the shape of the material. For that, we have used the scanning electron microscopy SEM technique to get an idea about what is the physical feature or the morphology of the material. And further, the morphology of the material was obtained from TEM technique. The SEM, scanning electron microscopy, this is a technique which can indicate what is the morphology of the sample at the micrometer level, whereas the TEM, this is a technique which can indicate what is the morphology of the sample at the nanometer level. So and from both of these techniques, we were able to confirm that this material yeah, has a sheet type of a structure. Sheet means two-dimensional structure. It's like you can imagine it's like a torn papers type of a thing. Then from the elemental mapping analysis, we can find out what are the constituent elements and where these elements are present in the sample. Subsequently, we have done a detailed XPS characterization. XPS stands for the X-ray photoelectron spectroscopy. And this technique gives information about what is the oxidation state of each of the elements present in the material and how the different elements are interacting with each other. For example, whether it is forming a NC double bond N bond or whether CC type of a bond, what type of a bond, it's a double bond or single bond or triple bond, what type of interactions are feasible between the different elements. So that is being illustrated from the XPS technique. And another thing is the XPS is a surface sensitive technique, which means that it probes the main surface of the material. And from the surface of the material, we can get an understanding of what are the elements present on the surface and what is the atomic percentage of the elements present on the surface. And since sulfur is present on the surface, we were able to kind of understand that sulfur is present at 3.27 atomic percentage on the surface of the sample. Then we did this experiment wherein the starch gets converted to glucose and fructose, which eventually gets converted into the 5-HMF, which is the desired product. And we did a detailed optimization of the reaction, wherein first we optimized the catalyst amount and found 10 milligrams is the optimal amount of the catalyst. Just like cooking, we need to optimize how much salt is good enough, how much chili powder is good enough, how much of dal should be put, how much water should be put. So we kind of optimize in the cooking, right, until we kind of come up with a well-known recipe. So similarly, here also we optimize the various things. Like first we optimize the catalyst amount, then we optimize the temperature and found 200 degrees C is the optimal temperature. Whenever optimal temperature means it gives the highest yield of the product. Then we optimized for the time, and then we did the experiments for all the different saccharides which we have it in stock. Then we did it for the various green solvents, and it's interesting to notice that all the green solvents are yielding the selective product, which is the 5-HMF, and among them, water is the best suited green solvent, which gave the highest yield, both for the monosaccharides as well as for the higher saccharides, which is the cellulose and sucrose. And then we did the recyclability of the catalyst, because our catalyst is heterogeneous in nature, and the beauty of heterogeneous catalyst is you can recover the catalyst and reuse the catalyst. So we did the recyclability or the of the catalyst, and we found that although we are able to recover the catalyst to quite a good extent, but still the HMF yield decreases over a period of time. This is because the HMF, it's prone to polymerization, and once it gets polymerized, it forms something called as the humins, which are insoluble products, and these humins stick on to the catalyst surface and block the active sites of the catalyst, and that reduces the yield of the yield of HMF over different cycles. However, the structural integrity of the catalyst is remains stable, which is proved by X-ray diffraction here. Then, since our entire process is green in nature, we did a detailed green matrix parameter analysis, because everything, whatever we do, we need to kind of have a clear-cut numbers. We are successful. How much successful? Like just in schools, the difference kids are being marked. Okay, how much, whether they got 80% or 70% or 60%. Even in colleges, we tend to do it that way. So here also, how green is our reaction? So we have to kind of determine it through the green matrix parameters. And the green matrix parameters include environmental factor, mass intensity, process mass intensity, solvent intensity, atom economy, reaction mass efficiency, mass productivity, and carbon economy. There are different formulas and definitions for all of these. And in the interest of time, I'm not going into those details, but nevertheless, we have applied these green matrix calculations and found that these are the values which are obtained, which indicate our reactions are green in nature. And the obtained 5-HMF was converted into other useful products, as I said earlier, using normal process in relatively decent yields. And this work was published in the journal Green Chemistry in 2019 with my former PhD scholar, Dr. Tripti Chabra, as the first author. And in yet another work, we have done a similar type of a thing, but here we have used a combination of Lewis and Bronsted acid sites on the graphitic carbon nitride. So this one, the graphitic carbon nitride, this was initially doped with boron, which indicates that this boron will give the Lewis acid site onto the graphite carbon nitride, and also the existing nitrogen atoms will give the Bronsted basic sites to the Bronsted and Lewis basic sites to the graphite carbon nitride. On the other hand, when the same thing is functionalized with SO3H groups, the sulfonyl groups, that will impart the Bronsted acid site to the catalyst. So the same catalyst has Lewis acid site, Bronsted acid site, and also the different basic sites. And this was used for the conversion of monosaccharides to 5-HMF, and we got some good results. That work was also published in Carbon Journal. In yet another work, we have taken hydrochar. Hydrochar is obtained from the waste orange peels, and we have functionalized this hydrochar with different functional groups like sulfonic, nitrate, and phosphate functional groups in order to get a heterogeneous catalyst, and that catalyst was used for the solventless synthesis of biofuel precursors. And this work was also published in Green Chemistry Journal in 2022. And this work also got some media attention during the time of its publication. And quite recently, in the beginning of this year, we have published another article in the journal Fuel, wherein we have taken niobium pentoxide and grafted it with sulfonic acid groups and used it for the solventless conversion of biomass derivatives to high carbon biofuel precursors. Now moving on to the second part of my talk, which is on organic transformation. So here what we have done is we have used the same graphitic carbon nitride, but here we have used an oxidized form of the graphitic carbon nitride and used it for the transfer hydrogenation reaction. Transfer hydrogenation reaction is a very important reaction in industries because the hydrogen source which is used is quite easy to handle, so that the possible casualties are minimized, and we can use mild reaction conditions in the transfer hydrogenation process to have an enhanced selectivity. So what we have done is we have taken the graphitic carbon nitride, which is similar material which I introduced earlier, and did a chemical oxidation of it. Then the oxidation process introduces the OH group or COOH group or the carbonyl group onto them, and these are the active sites which do the transfer hydrogenation. And this oxidized form of graphitic carbon nitride was used as a metal-free heterogeneous catalyst for the sustainable transfer hydrogenation under mild reaction conditions. This is how the material was prepared. First, we did prepare the graphitic carbon nitride using a simple calcination, which is the polymerization reaction, and then using H2O2, which is the oxidizing agent, in the presence of HNO3 and H2SO4, we prepared the oxidized form of graphitic carbon nitride. And similar to the previous work, we did a detailed characterization of the material using XRD, Raman spectroscopy, FDR spectroscopy, and TGA to understand the presence of the functional groups, as well as the structural integrity, what type of structure is formed of the catalyst, and the thermal stability of the catalyst. Then we did a morphological analysis using SEM and the TEM techniques, which again indicated a sheet type of morphology for the sample. We did an elemental mapping, which indicates what elements are present and where they are located within the sample. Then we did a detailed XPS analysis to understand what are the constituent elements and what is the oxidation state of those elements and how the different elements are interacting with each other. Then we took this reaction wherein the 4-chlorobenzaldehyde gets converted to 4-chlorobenzyl alcohol in the presence of 2-propanol. The 2-propanol is being used both as a solvent as well as the hydrogenation agent, which is the transfer hydrogenation agent, in the presence of our catalyst. So what happens is these two hydrogen atoms, this kind of gets connected over here to form this alcohol group, 4-chlorobenzyl alcohol, and as a result, this gets converted to acetone. This is the transfer hydrogenation reaction, and for one of the conditions, we got the best yield, which is about 92%. And we did a detailed substrate scope study wherein we changed the different carbonyl groups and did the same reaction, which indicates the universality of our catalyst and the process. And we tried with the electron withdrawing groups, electron donating groups, aliphatic groups, aromatic groups. So we tried with various different groups, and the reaction was going successfully in all the cases, which indicates the universality of our catalyst and the process. Then we again evaluated the green matrix parameters. Herein we evaluated the environmental factor, atom economy, mass intensity, process mass intensity, reaction mass efficiency, and also the carbon economy. And we got relatively good values for each of these cases. And this work was also published in the journal Green Chemistry with my former PhD scholar Priyanka Chaudhary as the first author in the year 2020. And this work also got some media attention during the time of its publication. Subsequently, we did another work wherein we have used the sulfonic acid functionalized graphitic carbon nitrate, which was functionalized with a different strategy and used it as a solid acid-based bifunctional catalyst for Navier-Stokes condensation and multi-component tandem reactions. And this work is also published in 2021 in Material Chemistry Frontiers. And last year we published another work wherein we have taken again the graphitic carbonitrate, but here we have done phosphorylation. It's a different type of functionalization onto the graphitic carbonitrate and used it as a sustainable, selective, and metal-free catalyst for the synthesis of primary amides. And quite recently, in the middle of this year, we published another work. Apart from graphitic carbon nitrate, we are also working in the area of boron nitrate, and we have functionalized this boron nitrate using hydroxyl groups and used it for the ipso-hydroxylation of aryl boronic acid. And this work was published in ACS, Applied Materials and Interfaces. And quite recently, few weeks ago, we have published another paper in Chemical Engineering Journal, wherein we have again used the boron nitride material with the functionalization of sulfonic acid group and used it for the synthesis of aromatic nitriles under mild reaction conditions. Now, moving on to the third part of my talk, which is on carbon dioxide conversion. As we all know, carbon dioxide is a greenhouse gas and it is kind of polluting the atmosphere, and it is also increasing the temperature of the earth, and it's causing the climate change problem. So if we can kind of convert this carbon dioxide into other useful products, it can address both the climate change problem and also we can get other useful products. So what we have done is we have prepared a catalyst, which is the boron-doped graphitic carbonitrate, and used it for this conversion of carbon dioxide to other valuable product. So here the carbon dioxide gets converted to cyclic carbonate. So basically how we do it, because we can insert this carbon dioxide onto epoxide to achieve cyclic carbonate. And cyclic carbonate is a very useful platform chemical which can be converted into polycarbonates and many other useful products. So what is the challenge here? Because the challenge is to do the conversion of CO2 at atmospheric pressure. There are already many reports which can do this type of conversion reaction under high pressure conditions, but we have used atmospheric pressure for doing this conversion. And how we have done it, having a bifunctional boron-doped graphitic carbonitrate catalyst, which has both acidic sites. The acidic sites come from the boron atom in the catalyst, and basic sites. Basic sites come from the nitrogen atom, which is present in the carbonitrate group. So what is the role of acidic sites? Acidic site activates the epoxide ring by opening the ring. So this ring needs to be opened. This can be opened by the acidic sites. You can imagine these are the key to open the ring. And then the basic sites promotes the conversion of CO2 to cyclic carbonate, because CO2 by itself is inherently an acidic molecule. So that kind of sits or gets adsorbed onto this basic sites and eventually leads to the conversion of CO2 to cyclic carbonates. This is how we prepared the catalyst. And similar to the previous cases, we did a detailed optimization of the catalyst preparation, wherein we have taken the boron in various different proportions from 1 weight percent to about 15 weight percent, and then did a detailed characterization using X-ray diffraction, FTIR spectroscopy, Raman spectroscopy, and thermogravimetric analysis in order to understand the successful preparation of the catalyst. We also characterized using SEM at the TEM technique to find out the morphology, and we found again in this case as well sheet type of morphology, because we were aiming for sheets and it's an established protocol, so we were getting sheets. And then we did a detailed XPS analysis, which indicates how the different elements present in this catalyst are interacting with each other and what are the oxidation states of the different elements present. Any
பழத்தை எடுத்து கொடுங்க. ஆனா தப்பு வந்துடும், அவங்க கரெக்டா சொல்லிருப்பாங்க. கெமிஸ்ட்ரி மேடம் தான் தந்தாங்க. அப்புறம்
Professor Dr. R. Selvakumar, please mute yourself.
Okay, I'll proceed. Fine. If you have any questions, I'll be happy to answer them all at the end. Then we did a detailed optimization of the catalytic process, wherein we first optimized the catalyst, wherein we found that 5-8% of the boron-doped graphitic carbonitrate is giving the best result. Then we optimized the catalyst amount, and we saw that 100 milligram is the optimized catalyst amount. We optimized the reactant amount, wherein epichlorohydrin was used as a model reactant, and we optimized it to about 20 millimole of this reactant. Then we optimized the temperature here. Again, we found 100 degrees C is the optimal temperature. We also optimized the time. And since we are using atmospheric pressure, the reaction takes quite a long period of time, which is about 60 hours. But nevertheless, we are not using the high pressure, which means that it's still sustainable reaction. We also need to use potassium iodide as a co-catalyst in order to enhance the activity of the catalyst. So, and we optimize the co-catalyst amount as well. Then we did the reaction using different reactants with varying substituents, and we found that all the reactants were giving their appropriate products, which indicates that the reaction is universal, and also the catalyst is not specific to a particular reactant, but it is more generic to a multiple reactants. Then we also deciphered the mechanism of the reaction. In the interest of time, I'm not going much into the details of the mechanism. We also did the recyclability study with and without the potassium iodide, which is kind of indicated here, because potassium iodide is soluble in water. And when we recover the catalyst, after the recovery, we wash it with multiple times with water to remove all anything which is sticking onto the catalyst. So in that process, the potassium iodide is getting lost in every cycle. So we have to keep adding that potassium iodide after every cycle. And we also studied the structural integrity of the catalyst, which indicated that the catalyst is retaining its structural stability. And this work was published in the Journal of CO2 Utilization by my former PhD scholar, Krishnan Chand. And very recently, we published another article in the journal called Fuel, wherein we have compared the catalytic activity of different graphitic carbonhydrates derived from different precursors for carbon dioxide conversion. And this will appear in one of the first issues of the Fuel Journal in 2024. Now moving on to the next part of the presentation, which is on photocatalysis. And when we do the photocatalysis, the holy grail of photocatalysis is how we can utilize the total solar spectrum for photocatalysis. And as we know, in the total solar spectrum, only 5% is in the UV region, whereas 43% is in the visible light region and 52% is in the infrared region. So how we can better utilize all the three regions of the sunlight for photocatalysis? So in this case, I would like to take an example of photocatalytic pollutant degradation, wherein we have designed and developed a catalyst, a single catalyst, which can do the reactions under UV light, visible light, and also near infrared light. UV and visible are no problem, but generally near infrared light photocatalysis is not so common and not easily used. But we have certain material called as this upconversion nanoparticles. These are new generation fluorophores which are capable to convert the NAR light into visible light. That means it absorbs the low energy light. NAR light, as we know, it's a low energy light, whereas visible light is a higher energy light. So the upconversion nanoparticle, it absorbs the low energy light and emits a higher energy light via nonlinear optical processes, as shown here. So this is the upconversion nanoparticle, which is the sodium yttrium fluoride. It can be sodium gadolinium fluoride or any other type of structure as well. Then and it is doped with lanthanide ions like ytterbium and erbium or any other ions. And when the NAR light is falling onto this material, this will undergo a nonlinear optical process and will lead to the emission of a visible light or even a higher energy UV light. And by tuning the identity of these elements, the lanthanide dopants, one is the activator, other is the sensitizer. And by tuning the identity, we can tune the wavelength of emission. For example, if you have ytterbium with erbium, it will give green emission. If you have ytterbium with holmium, it will give red emission. If you have ytterbium with thulium, it will give blue emission as well as UV light emission. So basically, when we compare and contrast the upconversion luminescence with conventional luminescence, the conventional luminescence, there's an excitation to a much higher energy level, then there is a non-radiative decay, and then there is an emission from another level to the ground level. So the emitted light has a lower energy compared to the absorbed light. On the other hand, in the upconversion luminescence, there are multi-photon absorption. So one photon gets absorbed from one level to the other, another photon gets absorbed from another level to some other level. And finally, the emission comes from a much higher energy level to the ground level, which indicates that the emitted light is having a higher energy compared to the absorbed lights. And in this case, what we have done is we have first prepared the upconversion nanoparticle, because this is going to be the NAR light active material. We have prepared it as sodium yttrium gadolinium fluoride and doped with ytterbium and thulium, which means that this will emit both UV light as well as blue colored light. And we have made it as a core shell type of particle in order to enhance the light emission. Then we have prepared another material, which is the n-doped ZNO. And as we know, ZNO is a semiconducting material and it's a UV light active semiconductor. And when we dope it with nitrogen, we are kind of tuning the band gap of the semiconductor. And in this case, we tune the band gap of the semiconductor to certain level that the emitted UV radiation from here gets absorbed by this n-doped zinc oxide. So we are kind of coupling these two to get together. The radiation which is emitted from here when the air light is impinging on it, that radiation gets absorbed here. Then another thing what we have done is we have decorated this entire system with gold nanoparticles, because gold is very well known for its surface plasmon resonance property, SPR property, which means that it can absorb the visible light and have the surface plasmon resonance. And this is a ternary nanocomposite because it has three components in it. And similar to the previous case, we did a detailed characterization of this material using various techniques, including UV-vis and upconversion luminescence, which indicates that this material is very good for the upconversion luminescence. We did a detailed morphological analysis using SEM and the TEM analysis, which again indicate that the zinc oxide has n-doped zinc oxide has a sheet type of structure, whereas this other material, upconversion nanoparticle, has a core shell type of a structure, and the gold has a spherical type of a structure. Then we did the detailed XPS analysis to understand what is the oxidation state of the different elements involved, because as you can see, there are so many elements involved in the overall material. So we studied the oxidation state of each of this material and how the different elements in the material are interacting with each other through XPS analysis. Then we did the reals and the UPS analysis in order to get an idea about the band gap of this material. Then we have taken one colorless pollutant, which is the tetracycline. We have purposely taken a colorless pollutant in order to avoid the photosensitization effect. Otherwise, the colored pollutant, we are unsure whether the effect is because of the catalyst or because of the photosensitization. Photosensitization is just fading away. If you get some cloth and it's kind of dark in color, and over a period of time, it becomes faded away and becomes lighter in color, paler in color. So that is the photosensitization effect. So in order to avoid that, we have already taken a colorless pollutant. And first we did the experiment under NIR radiation, and we found one of the sample AZU05 gives the best photocatalytic activity, which indicates that the photocatalytic activity is mainly because of the upconversion nanoparticle present in the system. Then we did the same experiment, but under visible light irradiation. And here the AZ sample gave the best photocatalytic activity. And here the main activity is due to the gold nanoparticles and its surface plasmon resonance. Then we again did the same experiment under UV light radiation. And here another sample, which is the n-doped ZNO, gave the best photocatalytic activity. This indicates that like the NZNO, which is having an appropriate band gap in the UV range, is the active semiconducting material for this purpose. Then we kind of did a detailed analysis of the mechanism based on experimental findings as well as literature reports, which indicates that when the NIR light is falling onto this material, it emits both visible light and the UV light. The visible light gets absorbed by the gold nanoparticle, which leads to the surface the plasmon resonance, and that leads to the degradation of the products, degradation of this pollutant. On the other hand, the UV light is emitted. The UV light kind of promotes the absorption of a photon here, which promotes this electron to move from the valence band to the conduction band. So holes are generated in the valence band and more electrons are available in the conduction band. And the electrons over there and the holes over here degrade the pollutant to smaller fragments, which are the degraded products. And this work was published in the journal Separation and Purification Technology in the beginning of this year with my former PhD scholar, Dr. Ajay Kumar, as the first author. Then we have done another work wherein we have utilized MAXenes and coupled it with graphitic carbon nitride and decorated them with plasmonic material, especially gold nanoparticles, and utilized them for the removal of pharmaceutical pollutant, which was published last year in Chemosphere. And in the previous year, 2021, we have published another paper in the Journal of Environmental Chemical Engineering, wherein we could control the kinetics of the visible light-induced photocatalytic performance of gold-decorated graphitic carbon nitride nanocomposites using different proteins. So if you use certain proteins, the rate gets accelerated, whereas if you use some other proteins, the rate gets decelerated. So we can control the rate of catalytic activity. Basically, we are controlling the kinetics of the photocatalytic activity. And based on this and few other works which we have done in the area of plasmonic photocatalyst, we have written a review article, and that review got published in the beginning of this year in Material Chemistry Frontiers. And we have also written another review article based on the plasmonic photocatalysis on TiO2 specifically, and that review was published in the journal Small 2 years ago. And moving on to the final part of my presentation, which is on nitrogen fixation. I was telling you about the nitrogen fixation, wherein we can take the nitrogen which is available in the atmosphere and get that converted to ammonia by using our catalyst, using water and natural sunlight. So what we have done is we have taken the inspiration from the leaf, because leaves are the best light harvesters, mainly because they have a small micro and nanostructures onto them, which can be observed from the scanning electron microscopy. And these micro and nanostructures kind of help in absorbing more light from the sunlight. So we have utilized that as a sacrificial template to prepare the leaf-inspired calcium titanate, and subsequently we have utilized sodium borohydride in order to kind of create certain vacancies or the defects onto this calcium titanate. Mainly, we have created some oxygen vacancy defects on the calcium titanate, and these defect sites are highly charged sites, wherein when the nitrogen molecule comes, it can sit on this defect sites, and eventually the triple bond between the nitrogen and nitrogen can be easily broken. And this is the SEM images of the saccharophilic leaf, one of the leaves which we have used. And this is the replica of the leaf in this calcium titanate. And you can see the good correlation between these two. Here, all the carbonaceous stuff of the leaf is gone, and only the calcium titanate remains because of the high temperature employed. If you do not use it, it will end up in some simple powder. Then we did other detailed characterization using XRD, Raman, and the XPS analysis. And from all the analysis, we were able to successfully prove the synthesis of the catalyst, and also the oxygen vacancies can be observed by some of these techniques, especially the XPS, because XPS indicates that the calcium titanate, the titanium in calcium titanate not only exhibits the +4 oxidation state, but also the +3 oxidation state because of the oxygen vacancies present in the sample. And we also did the EPR analysis in order to understand the vacancy formation. We did a detailed HRTEM analysis again to understand the vacancy formation and more details about the sample. Then we first utilized the sample for hydrogen evolution, wherein water was used as the solvent and the hydrogen got evolved from the water. And subsequently, we used it for the ammonia production, and we got relatively good amount of ammonia using this catalyst. Good means moderate to decent amount of ammonia. Then we did some theoretical calculations, in collaboration with the group of Dr. Saswata Bhattacharya. These are the density functional theories, the calculations, which supports the experimental results. Then based on all this, we have deciphered firstly a mechanism for the hydrogen evolution, and subsequently another mechanism for the ammonia fixation. And we get an STH efficiency of 1.17, and the ammonia of nitrogen fixation to ammonia was 4 times higher in the defect-rich samples compared to the pristine samples. And this work was published in the Journal of Material Chemistry A in 2021. And this also got some news media attention during the time of its publication. Then we recently did another work for the ammonia fixation, wherein we have utilized strontium titanate, and by tailoring defects onto the strontium titanate, we were able to achieve good photocatalytic nitrogen fixation. And in this case, we have utilized it in pure water. And very recently, just a few weeks ago, we published another article wherein we have utilized tungsten doped bismuth molybdate nanosheets, and wherein we have regulated the oxygen vacancies to produce higher amount of photocatalytic nitrogen to ammonia. Then based on these and few other works which we have done in the domain of perovskite oxides, we have written a review article for ACS catalysis, and this was led by my student Ashish Kumar, and this was published in the year 2020. Our work was also highlighted on the front cover of ACS catalysis. And since our group is working extensively in the domain of defect engineering and vacancy engineering, we also wrote another review for vacancy engineering semiconductor photocatalyst, and this was published in Advanced Functional Materials. Both of these reviews were written during the lockdown period. First review in the first lockdown and second review in the second lockdown period. And finally, to conclude, our group is extensively working in the area of heterogeneous catalysis for energy and environment. And today I touched upon some of the activities of our research group in the domains pertaining to biomass conversion, organic transformation, carbon dioxide reduction, and pollutant degradation, and I coupled the hydrogen evolution and nitrogen fixation in one single example. And once again, I'd like to thank all the members of my research group, faculty colleagues, and staffs at IIT Mandi for their kind support, research collaborators both within and outside IIT Mandi, and also our Advanced Material Research Center, which is a centralized instrumentation facility. Our facilities are open to all on a chargeable basis. So if you are interested to use any of our facilities, you may contact me. I'll put you in touch with the concerned office staff, and they can coordinate with you. And our charges are much lower compared to the several other educational institutions. And finally, I would like to thank also the funding agencies who have sponsored our work. And another word of advertisement that I have recently joined this new Journal of Chemistry. It's an RSC journal as an associate editor. So if you have any good publications, potential manuscripts for publication, you may please consider submitting to this journal. I also serve in the editorial advisory board of ACS ESNT Engineering. So if you have some other work pertaining to environmental science and technology, you may consider submitting to this journal. And finally, I would like to thank you all from IIT Mandi side. Thank you. Thank you very much. And thanks to Kavita and the other organizers for giving me an opportunity to talk to you all. Thank you.
Thank you, Professor. Thank you. A very interesting topic and very interactive. Now it's time for interaction.
Yeah. If there are any questions, I'll be more than happy to answer.
Sometimes the professors will post the questions in YouTube.
Oh, okay, okay. So someone can read it for me.
Yes.
Yeah, one question I can read. Dr. Murali Rajaram has asked. So this is about how to differentiate photocatalysis and normal fading you mentioned. So photocatalysis, it requires a catalyst, and normal fading doesn't require a catalyst, but both will require light. If there is a dye, whether it is in the clothes or even if you keep a simple dye in the sunlight over a period of time, it will fade away. The color will it will decolorize. So this is a normal process, which is called as the photosensitization in the technical terms. On the other hand, if we take the same type of a dye and keep it in the sunlight or any light source, and it is not changing the color unless until we add a catalyst, then it is photocatalysis. Because if we add a catalyst, then it's the catalyst which is interacting with the light, and because of this oxidation process which is happening, that will degrade the pollutant, which means that will decolorize the pollutant. So that is photocatalysis. Otherwise, it is a normal photosensitization. There is no catalyst. So if there is no catalyst, no catalysis. That's a good question.
Yes. Another question from Arjun. Okay. How to choose the material for visible light photocatalytic activity?
Yeah. So there are first and foremost, we need to see what is the band gap of the material. Band gap means what is the valence band energy level and what is the conduction band energy level. So that is very important, and the band gap should lie in the visible light region in order for the material to be visible light active. Another is band edge position, because this can be like there is an axis, you can imagine the y-axis. So this can be, the band gap can be 2.3. This is also 2.3. This is also 2.3. The space between these two is the 2.3 electron volts. So it is the same space, but whether it is here, what is the band edge position? What is the we need to correlate it with the reduction potential. So with what is the potential versus the NHE, normal hydrogen electrode. So whether it is this or this or this. And what is the application? And depending on the application, we'll have to choose the catalyst accordingly. So both the band gap means how much distance this exhibiting between the valence band and the conduction band. So this is the band gap, and whether the band edge position is whether it is this way, or this way. Both are important.
Another question by Dr. R. Mahalakshmi.
Okay.
Is it possible to carry out photocatalysis in solid state instead of solution state?
Solid state, our catalyst is in the solid state, but we have to disperse the catalyst is into some medium. We have never tried, or we have not done anything in the entire process in solid state, and I'm not sure it is feasible also or not. But pretty much most of the people do it in the solution state.
Okay, Professor. Any other questions? They will mail you.
Yeah, sure.
Yeah, another question from Arjun. Thin film also possible to use photocatalytic activity?
Yeah, it is possible. There is a lot of work which has been done on thin films. So thin film is coated onto some solid substrate like quartz or even simple microslide glass or something, and it can be dipped into the solution, and photocatalysis is feasible. Basically, we need to expose the catalyst to the light. If it gets exposed, it can do the photocatalytic activity.
Another question from the Professor Sashireka. How to prevent the metal nanoparticles from its oxide duraplasmonic?
Plasmonic based catalyst or functionalization. So metal nanoparticles, in our case, as you can see, metal nanoparticles, we have used gold nanoparticles. Gold is a very stable, noble metal. So gold doesn't get oxidized. If gold gets oxidized, all our ring or chain will not be gold anymore. It will all become gold oxide. Other metals such as nickel, copper, and all are prone to oxidation. So that we have not worked on it, but there are different strategies, like we can do a surface functionalization, capping of the nanoparticles, and those capping or surface functionalization will prevent them from oxidizing. Yeah, in that way we can do it. Capping is the technique to go for.
Same professor asked how to prevent the metal nanoparticles from its oxide during plasmonic based catalysis or functionalization.
Yeah. Plasmonic is exhibited only by few selected metals like gold, silver, and copper to a certain extent in visible light. There are other materials like aluminum exhibit plasmonic in UV light and all, but we are using gold based plasmonic, and gold is stable, so it's not a problem. Without functionalization, we can handle it.
Thank you, professors. Thank you. You can mail your questions to the professor. He will answer. And
Arjun has asked how to calculate the band edge potential. So band edge potential, these values are normally available. So the reduction potential, these are standard values. So from some standard textbooks, you can get those values. That is one thing. And how to measure or how to determine it for your catalyst. So that can be done using various different techniques like Mott-Skotsky plot. That is one technique to kind of get an understanding about the band edge potential. So there are a few such techniques where you can use to experimentally determine the band edge potential.
Thank you all.
Yeah, welcome. If there are no more questions, I would also like to thank all the participants and thank the organizers once again.
Yes, thank you, Professor. Good evening, professors, and to all the participant professors. Today, professors started with the presentation from need of sustainable development, whether we need a conventional approach or sustainable approach, and the 12 green chemistry principles and SDG goals. And as he stated the different SDG goals, what he is adopting in by their students. Yes, we are also following the SDG goals for in our curriculum for NAC purpose. Yes, we are doing this because for our criteria one, we have to state whether our syllabus is covered all the sustainable goals, development goals.
Okay.
Yes, thank you. And he next he narrated the graphite carbon nitride material and biomass valorization and organic transformation. And the another work by his student that carbon dioxide conversion, pollutant conversion. At last, he stated the nitrogen fraction fixation done by the student, and many publications published by the students. Is really, it's very informative and very useful to all our research communities, professors. Thank you, professor. Now, today is the final day. I have to thank all the participants, and you are the chief guest for our valedictory function also.
Okay.
Yes. And it gives me an immense pleasure and a great joy for me to extend a vote of thanks to all the for me to extend a vote of thanks to all those who have contributed in one way or the other make to this program as a grand success. Yes, on behalf of Department of Physics and my own behalf, convey deep regards to our secretary, giving a continuous support in all our academic activities. Yes. I thank our former principal and present principal for encouragement and guidance for providing a stimulating environment for such educational developments. I offer a gracious thank to our HOD Madam, Dr. S. Aram, Yes, Dr. Aram, whose strong spirit to attain accuracy and perfection in work, bold courage, enormous support and guidance in academic pursuits serve as an inspiring faculty to the students. And it's time to thank our resource persons. Yes, to brighten anywhere, it is necessary to brighten everywhere. Yes, to shine anywhere and everywhere, it is necessary to develop academic excellence, high scientific thinking, and need to involve in brainstorm activities. Yes, all our resource persons, Dr. Gunashekharan from Madras University, and Dr. Raghunathan from CBNR Coimbatore, and Dr. Pradeep from Mumbai University, and Dr. Anantaraj Shankani from IIT Kanpur, and Professor Venkatakrishnan from IIT Mandi. Yes, their motivating force and illuminating presentations to us gives an interest in taking our research careers to a greater heights. Yes. Now, I would like to express my sincere thanks to the participant professors from various institutions. Finally, I would like to take this, also like to extend my gratitude to our department professors who have been my guiding lights, and their unwavering support has been instrumental in growth and development in our department activities. Yes, finally, I thank my non-teaching staff members also. And at last, I thank my submitting glory to the God Almighty for making the program a resounding success. Once again, I thank you all and one and all present here. Thank you.
Thank you, Kavita.
Thank you.
Thank you for the opportunity. Yeah, nice talking to you all. Thank you. Goodbye.
Thank you. Goodbye.
Goodbye.
Thank you, professors. Please kindly post your feedback within a half an hour, and we will send the certificate within a couple of weeks. Yes, it's take time because there are more participants, and we are preparing the certificate now, and we will send it within a couple of weeks. Thank you, professors. you.